Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to give an example of how to use kind of a graphical analysis to solve problems involving motion or kinematics. So in this example, what I want you to imagine here is this. At t equals 0, right, this car is sitting here at rest. However, the driver is going to hit the gas and the car will accelerate at 20 foot per second squared, which we're going to assume to be constant in this problem. 500 feet away is this red car traveling in the opposite direction at 40 feet per second. And what we're going to try to do is calculate how many seconds is going to go by and how far will this black car have traveled when he passes the red car. So it's a motion problem, and it's a problem about velocity and position and acceleration. These are vector quantities. So the first thing we should do before we do anything else is put a coordinate system in this problem. You can put a coordinate system anywhere you like. I think the location of this black car would probably be a pretty good place to measure x from. Since it's a one-dimensional problem, I'm just going to put the x-axis here. That's really all we need. All right, now I'm going to start talking about the motion of the cars. So we've got three things to consider: velocity, position, and acceleration. And I usually start by drawing an acceleration graph. So I'm going to talk about this car now. So car on the left. In fact, this is car 1 here. I'm going to talk about the acceleration graph. This car's acceleration is 20 foot per second squared, and it's constant. So if I were to make a quick sketch of that, that would be pretty easy graph here, and that's at 20 in units of foot per second squared. Right, and that's going to be good to sometime. I'm just going to say t now. We're going to leave that kind of generic. Right. Next graph, the velocity graph of car 1. So the velocity graph is going to look like this. For starters, get the intercept. At t equals 0, how fast is the car moving? Well, it's not. So it goes through the point 0, 0. And again, this is velocity against time. The velocity is increasing at a constant rate. So that's going to give us a linear graph. You know, after 1 second, that car is going to be going 20 feet per second, right? And then 40 foot per second, and so forth. So that's going to give us a linear velocity graph out to, again, the same time, t. Now, these graphs are related by the following relationship. We know that acceleration is delta v over delta t. Right, so delta v is equal to acceleration times delta t. So in this example, the acceleration times delta t, that's that area right there, and it's equal to 20t. And the initial velocity is 0, so this is going to read v minus 0 equals 20t. The units are consistent, so I'm going to go just put NCU here, which stands for note consistent units. So the equation for that line is v equals 20t. Right, now, with our velocity graph linear, now when I do my position graph, that one's going to have, again, a property that I call concavity. That's going to give us a concave graph. And it's going to be concave up, so it's going to look something like this. And again, the reason why I've made previous videos about how to draw these, if you're not sure why that's concave up, I'd suggest go back and look at some of the videos about graphing position against time. But basically, it's because the speed of the car is increasing. And we can get the equation from this by using this area right here, because velocity is delta x over delta t. Therefore, the delta x is velocity times time. That's true as long as that's an average velocity. On this graph, the average velocity times time is equivalent to that area right there. So this is going to be x minus 0 equals. Now this area is going to equal 1/2. The base is t. The height we know how to calculate. We don't have a number, but we do have an equation for it, which is 20t. And therefore the equation of motion for this car is going to be x equals 10t squared. All right, so what we have now, we have the equation that describes velocity against time and position against time for car 1. All right, let's talk about car 2. So car 2 is not accelerating. It's moving at a constant 40 foot per second to the left. So because it's not accelerating, I guess I'm going to skip the acceleration graph and just go into the velocity graph. All right, so velocity against time for car 2. The velocity of car 2 is constant at 40 foot per second, but it's left. So in terms of the coordinate system I have defined, I have right positive. That velocity would be negative 40 foot per second. Okay, these are units of foot per second out to some time. We'll just say t. My position graph for that second car, right, x against t. All right, let's talk about the intercept first. At t equals 0, car 2 here is 500 feet away. So this is up here somewhere, 500 units of feet. However, the x-coordinate is decreasing with time. Right? So this has a negative slope to it. Oops. Do a better job sketching it than that. You know, maybe something like this. Now, I'm not sure where to... For sure, they're not going to cross at a negative value of x. So this is going to be good out to here somewhere. Now, as far as how do we get this the equation for x here? Well, this area right here will give me the delta x. The delta x is going to be given by this area, and it's going to be negative because the velocity is negative. So delta x is going to equal negative 40t. So the negative 40 is coming from that on the graph, and then the time is coming from that. Now, delta x is x final minus x initial, so this is going to be x minus 500 equals negative 40t. It's pretty easy to solve that for x. X is going to equal 500 minus 40t. So we now have velocity and position equations for both cars. The next step is just to note this. They're going to cross, you know, somewhere in the middle here at some value of x. And when they go past one another, their x coordinates are equal. That's going to allow us to write this out, that this 10t squared has to equal this, 500 minus 40t. Okay. And that thing's quadratic. So I'm going to take a moment here and solve that. First, I'm going to note that everything's divisible by 10. So I'm going to rewrite that. I'm going to divide everything by 10, move everything over to the left, and that's going to give us t squared plus 4t minus 50 equals 0. I'll take a minute, pause this, and I'm going to get a calculator, wash that through the quadratic. Okay, I'm back. I got 2 roots out of it. I got 5.3 for the first root. I know I had a negative number for the second root, so I just threw that away because in these equations, time started at 0. So these cars should cross paths after about 5.3 seconds. We can calculate the x-coordinates using either of the 2 equations that we found. I'm going to go ahead and just use this one. X is going to equal 500 minus 40t. And I'm just going to note that the units are consistent. All right, and I got x equals 288 feet. Oops, I'm going to run that again because I think I screwed up on that calculation. 500, that can't be right, minus 4 times 5.3. I'm sorry, 479 feet. Write it up here. X equals 479 feet. All right, curiously enough, okay, I'm going to recalculate that again. I was looking at that. That wasn't making sense. Sorry, let me run that one more time. I got to write this out a little bit better. Okay. X is going to equal 500 minus 40t. When we put the 5.3 in, I had only put in 4t, so I screwed that up. Sorry. 500 minus 40 times 5.3. 288 feet. That's what I get out of that. So they're going to cross at about x equals 288 feet. So, important points of this video are how to draw the acceleration, position, velocity graphs, like this stuff, right, for each car in the same set of coordinates. And then another important point, how to use the acceleration information to come up with an equation for velocity, and then to use that to come up with an equation for position, and again for each car. And then how to use those equations to solve the problem. In this case, we take note that when these cars cross one another, their x coordinates are equal. Hope this video helped demonstrate these concepts. Have a great day.